Mars, for instance, was a habitable place. Could be that life arose there. We're all Martians.
Hello, and welcome to Instant Genius, a bite-sized masterclass in podcast form. I'm Jason Goodyer, Commissioning Editor at BBC Science Focus. In this episode, we catch up with science writer and long-time BBC Science Focus contributor Marcus Chown to talk about the biggest unsolved mysteries in cosmology. So, Marcus Chown, welcome to the podcast.
Thanks for inviting me.
Thanks so much for joining us. So, today we're talking about the mysteries of cosmology. So, why there's no question that over the years we've developed a pretty impressive picture of the universe. But as always in science, there's always lots to learn. So I thought the best place to start then, we've established that the Big Bang was the start of the universe. But what does that mean and how did we figure that out?
Well, I ought to tell you that physicists or astronomers have been dragged kicking and screaming to that idea, because obviously once you know that the universe had a beginning, then everyone says what happened before. So most people were wedded, or before the Big Bang idea was proved, most physicists were wedded to the idea that the universe had existed forever. But basically the universe, the building blocks of the universe are galaxies, 2 trillion of them, of which our Milky Way where we live is just one of them. And they're all flying apart like pieces of cosmic shrapnel in the aftermath of some titanic explosion. And if we run that expansion backwards, in our minds, like a movie in reverse, we come to a time 13.82 billion years ago when everything was compressed into a small space. And when you compress anything, it gets very hot, as anyone who's squeezed the air in a bicycle pump knows. So the Big Bang, this explosion, was a hot Big Bang. And the evidence of that is in the room where we are now, because the afterglow of the Big Bang, the afterglow of the fireball of the Big Bang, is all around us. So incredibly, 99.9% of all the photons, those are particles of light in the universe, are tied up in the afterglow of the Big Bang, and only 0.1% come from the stars and galaxies. That fireball light has been degraded by the expansion of the universe to lower energies, and it appears at microwave wavelengths, the wavelengths used by your phone, by a microwave oven, that kind of thing. So that's why we can't actually see it. But if we were to be out in space and we were to have glasses, magic glasses that could see microwaves rather than visible light, we would see the entire universe glowing white, not black at all. Everything would be white. It'd be like being inside a giant light bulb. And that afterglow of the Big Bang, which is the final proof that it happened, is the most striking feature of the universe.
And that's still something that astronomers study now, isn't it, with special instruments?
Yeah, I mean, it turns out that imprinted on this afterglow is basically the universe beginning to go from a uniform state in the Big Bang to a clumpy state. So today it's in a very clumpy state, with galaxies and big gaps in between. But in the beginning, it wasn't like that. So we can actually see the seeds of structures, the seeds of great clusters of galaxies impressed on this afterglow. So when I said you look at the sky and it should appears white all over, there were slight fluctuations in that whiteness, and those fluctuations are due to matter being slightly clumped. So we can see the beginning of the structures in the universe forming. So after that time, anywhere that was slightly denser than average had slightly stronger gravity and pulled in material slightly faster. And in a process which is kind of like the rich getting ever richer, the galaxies like our Milky Way formed.
Yeah, so I think the obvious question that someone as a curious scientist is going to... Obviously, that's took a lot of really clever people a long time to figure out. But you're going to think, well, what happened before the Big Bang?
Exactly, and as I said, this is why nobody wanted to believe in the Big Bang. I mean, they really the prevailing idea, the competing idea, which you've probably all heard, the steady state theory, which had been promoted by the British physicist Fred Hoyle. This said that the universe has basically existed forever, and it, which if that's the case, you don't have to worry about the beginning. But of course, once we began to be able to look a long way across space, so when light actually is incredibly fast, but on cosmic distances, it kind of crawls like a snail towards us, So when we look at very distant objects, billions of light years away, we're seeing them as they were billions of years ago. And the steady state predicted that the universe should look exactly the same back then as it does now. Well, it doesn't. There are things, for instance, called quasars, which were discovered in 1963. These are basically superluminous galaxies which are pumping out hundreds of times more energy than a typical galaxy. We now know they're powered by supermassive black holes, and they existed in the past, but they don't exist today. So they were the proof that the universe has actually changed and it's evolved.
So how about this idea of inflation, sort of eternal inflation as it's called?
Yeah, well, okay, so we have this basic Big Bang that we know is true, right? We know that the universe began in a hot, dense phase and has been expanding and cooling, and the galaxies congealing out of that cooling debris. We know that's true. We know that's true because of the existence of the fireball radiation, what we call the cosmic background radiation, which is everywhere. So we've got the evidence of that. But the Big Bang theory conflicts with our observations in three major ways. So you just mentioned one of them, but I'll just quickly say that we need an awful lot of what's called dark matter, invisible stuff that has, we can feel its gravity, but we can't see it. And we also need another thing called dark energy, which we often cover in Science Focus, stuff with repulsive gravity that fills a lot of the universe. And a third thing so basically you have this Big Bang model, which is hot, dense phase, universe expanding and cooling. We have to bolt on dark matter, dark energy, and as you say, inflation. And the reason for inflation is, so I say, inflation was a kind of super fast expansion that happened before the Big Bang. So if you imagine like the explosion of a nuclear bomb compared to a stick of dynamite, the nuclear bomb would be inflation, and the explosion of the dynamite would be the sedate expansion that's taken over since. The reason we need this is because when we look at this afterglow of the Big Bang, the whole sky appearing white, there are correlations between bits of the sky which are 180 degrees apart. But if we run the expansion of the universe back to the time when that radiation was formed, about 380,000 years after the moment of creation, we find those regions could not possibly have been in contact. There was no way that any signal could have gone between them. So how do they know to be at the same brightness, the same temperature? So what we've realized is there had to be a super fast expansion very early on. And so that would mean that these regions would have been in contact when we don't think they were, and this is inflation. So inflation, if you want the real description, it's a really unusual state of the vacuum. Okay, so the vacuum we think of is empty, but in quantum theory, the vacuum is not empty. But this is a weird state of the vacuum with actually repulsive gravity. And this repulsive gravity causes this vacuum to expand. So in the beginning, there was literally nothing but this vacuum. It's called the forced vacuum or the inflationary vacuum. But it expanded because it had this repulsive gravity, and it created more of itself. So it's like the ultimate free lunch. You've got some banknotes between your hands. You move them apart, you get more banknotes. So basically, inflation creates more and more of this vacuum for free. But as it expands, it's what we call a quantum thing, and quantum things are unpredictable. And so all over this ever expanding, faster expanding nothingness, the little tiny bits decay into normal vacuum, so the vacuum that's all around us today. And all the energy of this higher inflationary vacuum has to go somewhere, and it goes into creating matter in these tiny little bubbles forming everywhere. And that matter is heated to millions of degrees. Those are the Big Bangs. So in this picture, the Big Bang is not a one-off. There are Big Bangs going off all over this inflationary vacuum, kind of like fireworks just going off all over the place. And we just happen to be in one of these Big Bang universes.
And that's sort of one of the ideas of the multiverse, which is known as the bubble universe. Is that right?
Exactly right. So if we're in one of these bubbles, it turns out that the vacuum between us and the next bubble is basically expanding so fast that we can never, ever have contact with that. So in effect, that's another universe, And and this inflation, unfortunately, goes on forever, because if you imagine these little bubbles are forming, imagine it's like a moth-eaten coat, right? So the moths, and the coat is expanding. The moths can't eat the coat fast enough. As fast as they eat the coat, more of it expands. So this inflation goes on forever and creates all of these disconnected bubble universes, Big Bang universes. Yeah, so it does actually force on us the idea of the multiverse. And that is a real downer, because the idea of inflation was that it was going to give us a theory of everything, not that we were going to, one universe, one explanation, not we were going to have this infinity of universes.
So let's go on to, you mentioned there, dark matter.
Yeah.
So this is another thing that's just been a mystery for decades now, isn't it? So how did we first come across it, and, where are we now?
I think you can actually say a century, because the first person who realised that there had to be a lot of hidden stuff was Fritz Zwicky, a Swiss-American physicist in California. But yeah, so everywhere we see evidence of the visible stuff being pulled by the gravity of something invisible. But the main reason for dark matter is that without it, we couldn't possibly be here. The Big Bang predicts that we shouldn't be here. So I told you that there were these slight density enhancements in the Big Bang fireball, and because they were slightly enhanced, they had slightly stronger gravity, they dragged in material faster. As I say, the rich getting richer, that kind of process. If you think of that process, it would take 10 times the current age of the universe to make our Milky Way. Okay, so we cannot possibly exist unless there is an enormous amount of other stuff whose gravity speeded up that process of gathering matter together. So it's roughly the dark matter, the invisible stuff, outweighs the visible stuff by about a factor of 6.
Yeah, and we still haven't figured out what this is, have we? There's been dozens of theories, WIMPs, tiny black holes, all sorts of things. So what do you think the current top contenders are?
It's just really hard to know. I mean, there have literally been hundreds of proposals. This stuff, which is clearly in this room with us now, but we can't. It doesn't interact with ordinary matter. It could be just give out very little light, or it could give out no light. And as you just alluded to, many theories of particle physics do predict the existence of stuff. There's a theory called supersymmetry that predicts a whole load of new particles, but all searches at the Large Hadron Collider in Geneva, in laboratories stuck down mines all over the world, have failed to find absolutely anything. Basically, you've got to wait until some bit of dark matter bumps into something that your detector, and note the vibration or something like that. That's what you've got to do. But since we've got no idea what the dark matter is, there's a very difficult to look for it. And as you say, all earthbound experiments have completely drawn a blank. So we don't really have much of a handle on it. But interestingly, you mentioned black holes there, and the very interesting thing about black holes is of all these hypothetical things, we know they exist. So in my mind, they are the least outrageous possibility for the dark matter. But we've done these searches called macho searches. There's a process called gravitational lensing. So when the light of a distant galaxy goes past a mass, it's kind of bent and focused, and we can see this effect. And we've used this effect to search for these things called massive compact halo objects. Could the dark matter be made of asteroids, dead stars, black holes? And the searches have actually drawn a blank. So there is still a possibility that black holes could be the dark matter, but there's a very small window of mass range where they could possibly exist.
Yeah, so let's go on to black holes then, another really fascinating topic. So as you said, a bit back, the Event Horizon Telescope actually made an image of a black hole. So, we know that they're out there. So what is a black hole?
Well, I mean, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. So incredibly, at the height of the First World War, Einstein presented his new theory of gravity in Berlin in a series of 4 lectures in November 1915. And I should tell you that he realised that gravity is the curvature of space. We can't see it because it's the curvature of 4-dimensional space-time, and we have 3-dimensional beings, we can't see it. So that's why it took the genius of Einstein to realise it. So you think the Earth is held going around the sun held on an invisible tether between the sun and the Earth, gravity. But in fact, the sun makes a depression or a valley in the space-time around it, and the Earth goes around the outer regions of this valley like a roulette ball in a roulette wheel. And I just should tell you that Einstein replaced the one formula that Newton had to describe gravity with 10. So finding the curvature of space, which is gravity, for any realistic mass, he considered impossible. But within a few weeks, a man working on the Western Front, on the Alsace Front, at a place called Mulhouse, found a description for the space-time around a compact mass. His name was Carl Schwarzschild, and he wrote this letter to Einstein, and Einstein was amazed to get a letter from the Western Front, and even more amazed to find that this thing that he thought was impossible was possible. But Schwarzschild hadn't finished. But beginning in 1916, he wrote to Einstein. He said, if the mass became ever more concentrated, the valley of space-time would become steeper and steeper and steeper until it became a bottomless pit from which nothing, not even light, could escape. And that's a black hole. So Schwarzschild is the person who discovered that. But then there follows an entire century where pretty much everyone thought these things cannot possibly exist. I mean, they are just too ridiculous. Einstein never believed in black holes because there's nothing to stop. Once a mass starts shrinking under its own gravity, there's nothing to stop it. And it will shrink down to a point. It will become infinitely dense. This is called a singularity. And when you get a singularity in any theory, it tells you your theory is broken. You've got to, you can't say anything sensible. So that's why Einstein hated this black hole solution, because he spent 10 years of blood and sweat developing his new theory of gravity. He didn't want to know within a few weeks that there was a flaw in it, But, nature has, despite the fact that we thought they can't possibly exist, these things, we have actually confirmed that they do. The actual definitive evidence was the signal on the 14th of September 2015, when gravitational wave detectors in America, so these detect ripples in the fabric of space-time, detected gravitational waves from the merger of two black holes, and the signal that they got was the definitive signature. But as you say, in 2019, an Event Horizon telescope, which is 8 radio dishes spread over the planet, there was one in Antarctica, one in Mexico, all over the place, they jointly observed the same object, which was a galaxy called M87, and which we believe had a 6.5 billion solar mass black hole in the centre. And the signals from all these telescopes are all identical, were flown together to supercomputers in Haystack in Massachusetts and Bonn in Germany. And on a computer, we were able to get the image we would have had we had a telescope the size of the Earth. And the bigger the telescope, the finer the detail you can see. And we got that amazing image of this donut, this glowing orange donut of material swirling down onto this black void, which was the black hole.
Yeah, in the office we call it the Eye of Sauron.
It is like the Eye of Sauron, yeah. But it took 3 more years to actually image the black hole at the centre of our galaxy, which is called Sagittarius A star. That was discovered in 51 years ago. And it's bizarrely, it's 1,000 times smaller than the one in M87, but it's 1,000 times nearer. So the two objects look exactly the same size on the sky. But the reason it took so long is because it's so much smaller, stuff whirls around it much, much faster. So it's kind of like very easy to photograph an elderly Labrador sleeping on your lawn because it doesn't move much. But try photographing a puppy that's flying about. The puppy's kind of Sagittarius A star, and the Labrador is M87.
So you mentioned there that a black hole not even light can escape from. So the big question then is, what's going on inside it?
Well, I mean, this is one of my bugbears, because in 1963, Roy Kerr, he's still alive, he's 91, he's a New Zealander, he's still publishing papers, and he did something that everyone thought was impossible. He found the shape of the curvature of space around a spinning black hole, so a realistic black hole. And it was the first solution to Einstein's equation for 47 years. And he then thought to himself, I need to find out what's the curvature of space inside the black hole, and he gave up. It's impossible. So it's not been possible for anyone to use Einstein's theory to predict what's inside a black hole. So everything you hear, oh my God, if you go into the center of the black hole, you're appearing another time, you're in another universe. This is all complete speculation. We have no idea. The theory predicts that there is a singularity, which is a point of infinite density, and for a spinning black hole, that's actually a circular thing. It's actually a circular singularity. But we know that singularities are impossible. So we're waiting for what's called a quantum theory of gravity, because we think that Einstein's theory breaks down and we need a better theory. But we haven't made much progress there. But that will tell us what's actually at the centre of a black hole. I should tell you that outside a black hole, space and time are highly distorted. So as you get near the black hole, in strong gravity, time slows down. So if you were to see someone falling into a black hole, they would be moved more and more in slow motion as they got closer to the point of no return, which is called the event horizon. That person, they would cross the event horizon into the black hole quite quickly. But from your point of view outside, it would take forever. And bizarrely, this distortion of space and time becomes even more ridiculous when you cross the horizon, because the direction of space and time switch. So the direction to the centre of the black hole is no longer a distance in space, it's a distance in time. So you can't avoid the singularity for the same reason you can't avoid tomorrow, because you can't. It's in the future. So
let's have a look at gravity then. You mentioned there this idea of quantum gravity. And we've got the standard model of particle physics, the three forces that explains the strong force, the weak force, the electromagnetic force. And they all have a particle associated with them. And we found those. There are several in the weak force, for example, aren't there? But when it comes to gravity, we haven't been able to find its associated particle. So what's the idea behind that, and why is that so tough?
The reason for that is that gravity is unbelievably weak. It's 1 followed by 40 zeros weaker than the electric force that is holding together the atoms in your body. It is so weak that I can hold my arm out and the entire mass of the Earth, with all of its gravity, cannot pull my arm down. That's how weak gravity is. So in terms of you're talking about the other forces, they have a quantum explanation. So we imagine that the forces arise because of an exchange of what we call force-carrying particles. So as you say, with the electromagnetic force that glues together the atoms in the bodies, it's this exchange of photons. And with gravity, it's gravitons. And weakness is associated with infrequency of interaction. So it means that because it's so weak, the gravitons hardly ever interact. And when you do a calculation, Freeman Dyson, the British physicist who lived in America most of his career, he did a calculation, and I think he realised that you would need a detector the size of Jupiter operating for more than the age of the universe to expect one graviton to interact with it. So I don't think we're going to... there is a lot of interest now incredibly, in maybe tabletop experiments that might be able to yield evidence of gravitons. But we have every reason to believe that the gravitational force, just like the other three, has a quantum explanation in terms of the exchange of gravitons. It's just weird that uniquely gravity can be described as geometry. Okay, so because everything falls at the same rate, you can imagine it's all falling, in the same curved space-time. You can't do that for the electromagnetic force, because the force that's experienced by a mass depends on its charge. So that's a different geometry for every charge. But in the particular case of gravity, which is a universal force that affects every single mass the same, there is this geometrical explanation. But that doesn't necessarily mean that there isn't a quantum explanation as well.
So a sort of another big mystery that physicists, particle physicists and cosmologists have been trying to figure out is is the fact that where is all the antimatter? Because the theories say that there should be essentially equal parts of matter and antimatter, but there's way more matter than antimatter.
Yeah. Well, first of all, we ought to say that one of the really shocking aspects of modern science is that only 5% of the universe have we seen. Okay, so the majority, the 95%, is this dark matter and dark energy. We don't actually know what it is at all, and the 5% is made of atoms. So we really haven't really seen much of the universe. But as you just said, that 5% should come in two types, because every single experiment we do with particles, when we generate a particle of matter, we automatically generate a particle of antimatter. So the electron has a partner called the positron, which has particular significance to Bristol, where Science Focus is based, because Paul Dirac, the Bristol physicist, is the person who predicted antimatter in about 1928. But yeah, so there is a clue to where the antimatter is, and that is there are 10 billion photons in the universe, particles of light, for every particle of matter. Okay, so that tells you that because when matter and electrons and positrons meet, they annihilate and end up as photons. So that tells you that in the beginning, for every 10 billion particles of antimatter, there were 10 billion and one particles of matter. And then there was this orgy of destruction, and pretty much all of it turned into photons, leaving this just one particle per 10 billion of matter. So there's a tiny, tiny asymmetry in the laws of physics, which must have resulted in all the antimatter vanishing. And really, when you think about it, that has to exist, because if it didn't exist, there would be no universe, because all matter would have been destroyed and annihilated if it was equal amounts of antimatter and antimatter. So the person who actually really discovered what has to be part of the solution is a woman called Chien-Shiung Wu, who was scandalously overlooked for the Nobel Prize in 1957. She did this tremendous experiment which everyone thought was impossible, and she found that there was a skewness to the laws of physics, that the weak interaction, the weak nuclear, one of the four forces called the weak force behaves differently when it pulls on particles which are spinning one way to the other way. Okay, and it's called parity violation. And there were great physicists of the day like Wolfgang Pauli bet their house that it couldn't possibly exist, and she proved it was correct. But the two theorists who predicted it won the Nobel Prize, and she didn't get a share. But somehow the solution has to involve that. So either there was a process in the Big Bang that produced a surplus of matter over antimatter, or there was a process that destroyed antimatter preferentially, but we haven't found it yet.
So let's finish up with a classic sci-fi favourite then, the search for alien life, particularly intelligent life.
Yes.
So a lot of people say, well, if it exists, surely at least if we haven't found it, it would have found us. So what's the idea there?
Well, it is a puzzle, isn't it? You know, why we haven't seen anything, but it's a big universe. If you look at life on Earth, you see that it got stuck at the single cell stage for a long time, about 3 billion years, something like that. And only in the last about 800 million years or 500 million years has it become complex. And that kind of implies that the step from single cell life to complex life like us is a difficult one. So it could be, and this is a problem that we're arguing from one instance, which is very difficult. It could be that there is a lot of life in the universe, but it's very simple. You know, it's only single. If it's like ours, it's single cell organisms, and there may not be much intelligent life. So we haven't seen any sign. But I mean, I just remember that one of the great books that got me interested in physics, and that was Carl Sagan's The Cosmic Connection. And I remember him saying that there were tribes in New Guinea who lived in separate valleys, and they spent their lives in these separate valleys, and they communicated with big drums. And he said, if you'd asked them, how would you communicate with an advanced civilization, a few valleys away, they say, use a bigger drum. And we are using radio waves, which we've only been using for a century. Almost certainly, other forms of communication might be used by extraterrestrials. And, we are just thinking, well, we'll just get a bigger radio telescope, and try and pick it up. So it could be that the extraterrestrial communication is whizzing through us at this very moment, and we don't know. But an interesting idea is from Stephen Wolfram. Stephen Wolfram is he's a physicist from London. He's a billionaire because he invented a computer language called Mathematica. And one of the questions is, where are they? And he thinks that if you look at our communications, they become more and more chaotic. Okay, so to squeeze more and more information into our radio communication, we make them more. There's less and less pattern. And so our signals, if you look at our phone communications and whatever, they're looking more and more like natural sources like the sun. So, we're looking for the interstellar equivalent of Radio 1. We're looking for a single carrier frequency that's modulated, but that may not be the way anyone is communicating. So there's lots of possible explanations, but I'm pretty certain that I'm pretty certain we'll find evidence of life in our solar system. I'm pretty certain of that because of the simple fact that there are meteorites that arrive on Earth from Mars. Something's hit Mars. A meteorite has been, ejected into space, circled around for a few million years and fallen on Earth. And it's possible for simple organisms like bacteria to survive inside this. And Mars, for instance, was a habitable place about 1 billion years before the Earth, or 500 million years before the Earth. We see evidence on the surface of rivers and seas. So it could be that life arose there first and came here, that we're all Martians. But certainly interplanetary panspermia, the idea that simple life could spread between the planets and is quite likely. And we can see quite a few places in the solar system where life could arise, in particular the subsea oceans of the Jupiter's moons, or Ganymede, Europa, Callisto maybe, and then of course Saturn's moon, Titan, Triton, or Uranus. There's quite a few places in the solar system where we could find life.
Mind-blowing stuff. Thanks for joining us, Marcus.
Thank you.
It's been a pleasure. Thank you for watching this episode of Instant Genius, brought to you from the team behind BBC Science Focus. That was Marcus Chown. To discover more about the topics we've just discussed, check out his latest book, A Crack in Everything. If you liked what you just saw, then please do consider liking this episode and subscribing to our channel.